I just thought that was just in my head, but I've recently found, reading up on brain research, and that it actually seems that we do our cognitive processing in a different part of our brain when we're talking versus when we're reading or writing or thinking. So I think it really is true. I'm not as smart when I'm speaking as I am when I'm writing. So the consequence is that when a topic comes up that I don't have I'm not either really familiar with or that I don't have good notes on, sometimes I watch the words coming out of my mouth. I think that doesn't make any sense at all. So bear with me when I get in those situations, and the solution for me to deal with that is take a moment to write down what I need to say, make a few notes, or just stop and think for a minute. So that's if I seem to go away for a minute, that's what I do. So having said that, are there any questions from last week so that I can confuse you further? Yes?
I think you mentioned in the lab that it's possible to weight the weight so you can kind of get a general solution to all your...
I don't remember the context, so what can you describe?
I think you mentioned that if you are a policymaker or something like that, you can take all the weight and come with a general, get a general solution. Or maybe it was just in my head.
I think what I was probably meaning to say was that if you're a policymaker and you know that different constituencies have different weights, different weighting functions, that you can aggregate those weights. And if you want to take into account the weighting function of environmentalists versus the weighting function of industrialists, you can have each of them come up with what their weighting scheme would be, and then you can find some way to average those. And in the multi-attribute value theory mode, the way that you average those would probably be a simple linear averaging based, based on whatever weight you want to give to each group. We'll see with the AHP, there's a different way to aggregate across groups. So the other reason why you might want to aggregate different weighting schemes is not just as a policymaker who's trying to take into account what the average public wants, but also if you're in a collaborative decision process and you've got, say, a bunch of stakeholders in the room, each of which has a different weighting scheme, so that you can also aggregate those weights. Does that make sense? Okay, so the analytic hierarchy process, or AHP for short, was developed by a person named Thomas Saati, S-A-A-T-Y. And he was not someone who was working within the framework of multi-criteria decision analysis per se. He was working in decision analysis and helping initially corporations and government agencies. Actually, I think his initial work was helping the U.S. negotiating team during one of the arms reduction talks with Russia. So he was kind of a consultant, and he developed this method more out of psychological research on how people make decisions and how people weigh different alternatives. And so it's a bit different from a lot of the other multi-attribute or multi-criteria decision analysis techniques. in that its motivation is not on constructing some kind of utility function or minimizing the risk of a bad outcome. It's more on trying to formalize the way people already make decisions. And when we do it formally, the sort of final aggregation step involves multiplying weights by attribute scores. So it looks like multi-attribute value theory, but the motivation for it is different. And the other aspect that's quite different is how it's the tools that it provides for eliciting opinions. So it's particularly useful for both for getting weights, which is a sort of inherently qualitative thing, weighting with different criteria, but also for even putting scores on criteria that have that are inherently qualitative, that don't have a natural numeric score. So it's very subjective. It's explicitly subjective. It makes no pretense of being objective because it's all based on people's opinions. But it's well, that's what it is. So to start with, I found a nice tutorial online that we'll go through, and then kind of come back. Well, I'll add some things that the tutorial doesn't cover, and come back and do something along the way. Yeah.
I tried to download it, and when I opened it, it said I can't open it, that the file's managed. From Gaucho Space. Did anybody else?
Yeah, I opened it last night.
Damn.
Okay, so anybody else have difficulties with it? Anybody else succeed at downloading it?
Works on a Mac.
I have a Mac too, so.
Well, okay, that was the question. Some PDFs don't. Well, when they open, they just don't display properly on the back.
I'll try it.
If you have trouble, shoot me an email and I'll send it to you. Because what the link on Gaucho Space actually goes to the place on the web where it lives. It doesn't. I didn't upload the file to Gaucho Space.
If the download gets interrupted, sometimes that'll happen. You get like a partial file, but it thinks it's the whole thing.
So okay, so the tutorial starts off with some motivation that we probably don't spend too much time on. Okay, so what is AHP? Well, it's used a lot, and in particular, it's used a lot in environmental decision making. I think, well, it just is used. It is used a lot. If you, especially in natural resource decisions, I think because the way of eliciting opinions is quite friendly to a stakeholder-driven process. So the hierarchy part is actually not unique to AHP. We didn't talk about this last time, but if you think about, there's some central problem, and we talked about having a bunch of criteria with which we're going to judge that problem. But each criterion, each sort of major criterion, can also have sub-criteria. Okay, and we can just as well do that using, well, in any other of these schemes as well. We can lay out this hierarchical format, but it's sort of in AHP it's the fact that this hierarchy exists and that you don't, if you've got a bunch of criteria, it's actually better to aggregate them into top level categories rather than trying to look at all of the criteria simultaneously. So this hierarchical thing is important, and we'll come back to that. The tutorial doesn't actually deal with the hierarchical So here's the example problem, choosing a new car. And so in this example, they are going to look at, so the objective is a new car. The criteria are style, reliability, and fuel economy. And there's 4 alternatives that they're going to look at. And notice that there's not really anything about cost here. So we'll come back to cost. So the objective, the criteria, and then under each criterion, we're gonna rank the 4 alternatives. And that's the general MCDA problem, and this is we'll look at the different way that AHP treats qualitative and quantitative data. So we talked last week about, how do you choose weights, right? And you can sort of, you can do this, you can throw darts, you can try to imagine in my head, well, what's the relative importance of style for, and try to fill out that whole vector of weights, which you could probably do with 3 criteria, but if you've got 10 criteria, we're just not very good at thinking in 10-dimensional space. So the power of the AHP, well, I'm getting ahead of myself here. Well, the power of the AHP is to try and come up with pairwise comparisons. Okay, so so you think about reliability versus style, which is more important. Well, reliability is more important. How much more important? Is twice as important. Style is 3 times as important as fuel economy. Reliability is 4 times as important as fuel economy. So this person probably isn't a Bren student, because fuel economy is not a very high priority there. Okay, but you could sort of think about. It's easier to hold 2 things in your mind at once and say, which one's more important? How much more important? Okay. And so, that. And so the standard scale that's used in AHP is a 1 to 9 scale, so that so you start with saying which one's more important, and then you say how much more important. So if they're equally important, you give it a score of 1. Moderately more important is 3. Strongly more important is 5. Very strong is 7. And extreme is 9. Okay, so if you sort of 9 is the most biggest difference you can imagine in terms of their relative. In this case, their relative importance. Okay, does that make sense? So then we assemble them into a matrix that looks like this. So the way we read this is to say that any entry in here, the fraction refers to the relative importance of so the importance. Let's see how to say this.
Rows versus columns. Style
It's
thrice as important.
Yeah,
as
it's rows versus column. But basically, so if the number is less than 1, that says that the row is less important than the column. Okay, so style is less important than reliability. So it's, or you could say style is half as important as reliability, right? And reliability is 4 times as important as fuel economy. Obviously, style is equally important as style. Okay. And then you can also fill in these values, right? If style is half as important as reliability, what should go in here?
2 over 1.
That should be 2 over 1, right? And so you get the reciprocals in the bottom half.
But we're still arbitrarily assigning those
Yeah, so these numbers are, somebody imagining, that's based on these decisions, which are, I sit down and say, how important are these?
So when I have 100 dimensional space, I need to sit down and classify that.
Yes, right, so as the number of alternatives, or alternative criteria goes up, the number of classifications goes up as the number of roughly as the number of criteria squared. Okay, so that's why it's important to if you have a lot of criteria, to group them into various groups, because then we don't actually have to compare every criterion to every other criterion. But that is one of the drawbacks of this approach, is that you can't let the problem get too large or it becomes intractable. Okay. Yeah, so they just fill in the rest of the matrix here, and so fuel economy is just 1/3 as important as style.
Bruce,
Yes.
what's the mathematician word for that matrix where the bottom half is reciprocal of the top half? It's not symmetric. There's another word I forgot what it is.
I don't know.
Yeah, I mean,
I mean, I'm sure there is a.
Yeah,
I'm sure
okay, I
there is
just
a
thought it was-
I'm sure there is a word for it. Okay, so, right, so we have this matrix now, right? And how do we turn that into a ranking of criteria? So the mathematician says, you take the eigenvector. Okay, so what is an eigenvector? How many of you have encountered eigenvectors before? Someone. Okay. So the tutorial really, the tutorial doesn't really talk about what an eigenvector is. So let me pause here and so if you have a square matrix A, okay, so in this case A is a 3x3 matrix, then I actually don't know if this is true for all square matrices, but at least for a large subset of square matrices, there exists a vector. So A is a matrix, W is a vector, and lambda is a scalar, so just a number. So there exists a vector W and a number lambda, such that if we take A and multiply it by this vector W, we get the same result as if we had taken the vector W and just multiplied it by this constant lambda. Okay. And W is called the eigenvector, and lambda is called the eigenvalue. Eigen is German for same. Okay, so what's important about this is if you take this vector W and you multiply it by A, you're going to change the magnitude of the vector, right, by this factor lambda. It might get, all the elements might get bigger, they all might get smaller, but the relative values in each of the elements of this new vector are going to be proportionally just the same as the original vector. So the shape of the vector isn't changed by multiplying it by this matrix. Okay, and it turns out it's useful in all kinds of surprising ways. If you take my population ecology class in the winter, you'll see it again in population models. And it turns out actually that there are, in general, there's not just one eigenvalue, an eigenvector for a given matrix. There are potentially, if A is an n by n matrix, there are potentially as many as n different lambdas and associated w's that have the same property. Okay. And the last thing to look at is that w, right? If we imagine, so say we found a w that satisfies this property, and then we just multiplied it by 2, right? That new vector would also satisfy this property, right? Because the constant factor of 2 just factors out. I mean, you can't, matrix math doesn't always translate into our usual intuition about how equations work. But in the case of multiplying by a constant, you can just factor out the constant. So, so really what there is there's an eigenvalue, and there's a family of eigenvectors that all have the same shape but different lengths. And so the convention usually is once you've found the eigenvalue, to take the eigenvector that has length 1, so that the sum of all the elements of W is 1, is the normalized eigenvector. So now, so this is if you took linear algebra, you would have encountered this. You may not have realized why it was useful, because in linear algebra classes they don't usually tell you why what they're doing is useful. But as I mentioned, it comes up from time to time in different places. So given a matrix A, there is a way. There are ways to calculate what W and lambda are. And when we go back to the tutorial, they present a way which is a way. It's not necessarily the best way, but it's one that's easy to do if you don't have access to software that has a command that says, so MATLAB and R, for example, both have commands that you give it A and tell it to give you the eigenvector, and tell it to find the eigenvector, and it'll give it to you. But why, if we have this weight matrix, or not this weight matrix, if we have this matrix of relative scores, relative values, why is the eigenvector of that matrix the weight vector? Okay. And I should add, because I said there could be multiple eigenvectors, so and each eigenvector has an associated eigenvalue. Though the pair that has the largest value of lambda, the largest eigenvalue, is called the dominant eigenvalue, and the associated eigenvector is called the dominant eigenvector. So it's actually the dominant eigenvector that we're looking for in this in the AHP. But let's look at this matrix A. So suppose that our pairwise choices were perfectly consistent with one another. Okay. Then, if we were to look at this, then this ratio of relative importance between style and reliability, for example, to say that style is half as important as reliability says that the weight of style should be half the weight of reliability. Okay, and so this matrix that we constructed, the elements are the weight of 1 over the weight of 1. So these diagonals are just 1. That's okay. And then, in this situation, we're saying what's the ratio of the weight of criterion 1 divided by the weight of criterion 2. And here we have the weight of criterion 1 divided by the weight of criterion 3. Okay, and so forth. Okay, so does that make sense, that logic? That these ratios, these relative importances, right, are also the ratios of, should be the ratios of the weights, if we knew what the weights were. Okay. So suppose we knew what the weights are, and we multiply this matrix by the vector of the weights. Okay, so this is a good chance to remember your matrix algebra. So how do we multiply a square matrix by, or a matrix by a vector? Right, lots of visual things. So so what we're going to get, because it's a square matrix, so we're going to get a new vector which has 3 elements, right? And the first element of this vector, we take the vector, flip it on its side, and do the pairwise multiplication. Okay, so we do that. We get W1. Let's give myself some more room here. So W1 times that is W1. W2 times that is W2. Sorry, W1
Plus W1.
plus W1. And then we do the same thing for the second row. We're going to get W2 plus W2 plus W2. Right? And so what we get is our new vector is 3W1, 3W2, 3W3. Okay. So this vector has the same shape. It's just been increased by a magnitude of 3. Okay. So in this case, the eigenvalue is 3, and the eigenvector is a set of weights.
But wouldn't we need to normalize it by the W vector
Well,
for our weights, or
yeah. So the actual so they all have so that the eigenvectors all have the same shape, and then to find the one that actually becomes weights, we normalize it so it sums to 1. Okay. So if we started off with this vector summing to 1, then that's what we would use as our weight vector. Okay. And so in general, if you've got an n by n matrix that's set up this way, then lambda is just going to be n, right? So if we had a 4 by 4 matrix, these would be 4s instead of 3s. Okay. So that's why, yeah, so if we've been perfectly consistent, if these values in this matrix really are the ratios of the weights, then we find what those weights are. And yeah, with a 3 by 3 problem, we could sort of work it out by trial and error. I mean, it really is just a system of, talking about a system of linear equations, but as the problem gets larger, it's easier just to ask the computer to calculate the eigenvector. Okay. Now, what if we haven't been fully consistent? Which in most cases we won't be, right? You know, the consistency says that, for example, when we compared the ratio of, say, the first alternative to the third alternative, so style to with preference of style to fuel economy should equal the preference of style to reliability times the preference of reliability to general, when you're doing these pairwise comparisons, since you're not keeping other things in mind and you're just looking at one thing at a time, there often are going to be inconsistencies. And in particular, so we said style to fuel economy is 3 to 1, and that should be style to reliability times reliability to fuel economy, right? That product is 2 to 1, right? So this is actually an inconsistent set of pairwise preferences. Okay. So in this case, all that math I just did on the board, it doesn't work out that way because these ratios aren't actually ratios of the weights. They can't be, because to be ratios of the weights, they have to be consistent. But it turns out that as long as these pairwise comparisons aren't too inconsistent, that the eigenvector of this matrix gives a weight vector that is most consistent with these stated pairwise preferences. And that's, there's a bunch of math in there that's more detailed than we need to go into.
Maybe I need to think of it on my own, but how will this matrix catch the inconsistencies? Because your lower triangle is the flip side of the upper triangle. So the inconsistencies this won't catch inconsistencies unless you try to do the extent, unless you let the logic progress not by flipping but by combining multiple pairs.
Right. So the flipping is all there. That's perfectly sensible, but it's you could call it transitivity.
Yeah.
Right. That's what fails here. That a fully consistent matrix, you multiply this value by this value, you get that value.
But so the transitivity, your eigenvector and eigenvalues will not catch the intransitivity because you are still just using the dot product.
Right. We'll talk later about how to measure there is a consistency index that we can look at once we get done. That basically comes from comparing the eigenvector or the eigenvalue of this matrix to the ideal eigenvalue, which is 3. For the eigenvalue of the consistent matrix, which is 3.
Yeah. Did it work out in this case because we didn't normalize the vector, or I guess maybe there's another weight vector.
Yeah. And as long as you're not an economist, it's perfectly fine to have inconsistent, pairwise consistent. Most of us aren't concerned with being 100% rational. It's the way most of us work.
That can sort of be thought of as a test of rationality, right?
Yeah. Yeah. And it could be, if we haven't talked much about how you actually, the process of collecting these data, in any multi-criteria decision problem, there's a long process of eliciting from the decision makers and from the stakeholders or whoever's involved what their criteria are. And especially if they're stakeholders who haven't necessarily thought rigorously about these issues before, there actually can be quite a bit that you can do to guide them, to help them think more rationally about what their preferences really are. So I don't know if this is used in that way to help people become more cognizant of the inconsistencies in their beliefs, but it could, it certainly could be used that way.
Bruce?
Yeah.
So the ideal eigenvalue is not the same as the dominant, right? The dominant could be higher than the ideal, or is it
Well, so the ideal eigenvector is, or I should say, maybe I shouldn't, ideal was the wrong word. The eigenvector, or the eigenvalue of a fully consistent matrix, which is what I worked out on the board, and that's just going to be n, the number of categories. And so the actual matrix, if it's inconsistent, is going to have a dominant eigenvalue that's different from that.
Would it be lower than that, or?
I think it's usually, it is, yeah, it's larger.
Large, yeah.
But don't ask me why, because I haven't thought about why, and I don't
Oh,
want to try and
sorry.
make up a story on the spot. Okay, so so if you're caught having to calculate an eigenvector, and all you have is Excel, and you don't have any of the add-ins to Excel that allow you to calculate eigenvectors automatically, here is a procedure to do it. Basically, you take your matrix, multiply it by itself, so which is squaring the matrix, calculate the row sums, and normalize them to 1, and then keep repeating that process until these row sums stop changing. So basically, so here's our matrix converted to decimals. Multiply it by itself to gives this new matrix. Take the row sums, which are here, normalize them to sum to 1. Okay, so that's sort of our first guess at an eigenvector. And then take this new matrix that we have squared once, that's a result of squaring our original matrix, square it again to multiply this matrix by itself, get a new matrix. Take the row sums, calculate normalize it, and compare it to the previous version, right? And so they differ by a small amount. But we could go one more time just to make sure. I mean, and, in reality, it's never that you have to do this an infinite number of times to converge to infinite number of decimal places. But 4 decimal places is probably about all we care about. And doing it one more time in this case doesn't give any additional difference. But basically, you keep repeating this process until this estimated eigenvector stops changing. And how long it takes sort of depends on the structure of the matrix. So there's the matrix, and here is our computed eigenvector. And so this gives us, because it sums to 1, this gives us the weights of style, reliability, and fuel economy. And so what we see, for example, is that style is a bit more than twice as important as fuel economy, but it's not 3 times as important, right? So it's sort of between 2 to 1, 3 to 1. Reliability is not quite twice as important as style, right? But so this is taking into account these inconsistencies in our original pairwise judgment. So these are the weights that sort of best represent these pairwise comparisons. Right. So we have these weights on these criteria. They sum to 1. So now what? So now we have to look at the alternatives. And it could be that we already had data on how each of the alternatives scored on each of these criteria, and then we could just do, for each one, take the value under style and multiply it by the weight, fuel economy multiplied by the weighted fuel economy, and that gives us the score for that, for the Honda Civic. Okay? But in this case, you know, for things like style and reliability, maybe we don't have quantitative data. You know, either it's a, you know, style is not really something that can be quantified in general, and in fact, there's no reason to express it even if you could quantify style, that we would all have the same preferences on style. Right? So we can do the same pairwise comparison, right? So we can now go to style and say, if I look at a Civic and compare it to a Saturn, which style do I prefer?
Saturn.
Okay, I prefer a Saturn. How much do I prefer a Saturn?
4 times.
4 times. So if I like the style of Saturn 4 times as much as the style of the Civic.
Civic's a model in Saturn's car company, so I guess, I don't know.
Well, I think I
Right?
mean, I think there was the original setup of this. I think they had specific cars.
Okay.
Let's see.
I guess that doesn't matter, but.
Yeah, let's see. Where is it? The Civic Coupe, the Saturn Coupe, Ford Escort, number no Clio. Oh, yes. Right. And so, you know, in this case, it's pure opinion, right? This is just, you're sitting there, you look at a picture of the Civic, you look at the picture of the Saturn Coupe, and say, you know, which one appeals to my sense of style. And, you know, or, you know, so this one really is a sort of pure opinion thing. Okay. And so again, we have now that we have 4 options, we've got 3, 4, 5, 6 pairwise comparisons that we have to make. Okay, so it's a little bit more arduous of a job. And similarly, we can, they suggest that we can do the same thing in terms of reliability. Okay, now, is this pure opinion? Well, you know, reliability, I mean, there are data about reliability. Consumers Union collects various different metrics of reliability. And then if you just sort of start Googling on the web, you find all kinds of people extolling or denigrating their cars based on how often they have to go to the shop. So, you know, probably what's going on is, you know, in this exercise, they're imagining that you're kind of integrating in your head your sense of what all this means. Of course, you could run, you know, within reliability, then you could actually say, well, what are the factors I'm going to look at for reliability, and actually, you know, do a, you know, get these values as the outcome of looking at, say, 4 different components of reliability. Okay, but for now, we're just going to say that you're sort of integrating it in your head, which, you know, so this reflects really your beliefs about reliability rather than any kind of objective data. So in each of these cases, we have those 2 matrices. We can calculate the eigenvector of each of those matrices, which gives us the relative values of the 4 cars with respect to style, with respect to reliability. Okay, so basically it says, you know, that we really like the style of the Clio, we really hate the style of the Escort, and then the Saturn and the Civic are in between. Reliability, the Civic gets the best score, then Saturn, then the Clio, then the Escort. Okay, so these then, notice that these sum to 1. So these are different than the utility functions we talked about on Thursday with multi-attribute utility theory or value theory, right? Those you typically said they were on a scale from 0 to 1 or 0 to 100. These are summing to 1.
It seems like from a data collection standpoint, this is sort of owners, like as you get the larger and larger numbers of different alternatives, you have to make, it's like a combinatorial problem, you have to make so many pairwise comparisons. And those are all preference. How are you going to get anybody to sit down and do that?
Well,
Like,
yeah.
I have an example. My brother does and they spent 3 hours with them inside the car, and they asked him, what do you think about the color, think about the quality of the I don't know, the handle. And then they go, they spent really 3.5 hours with them, and they collect all this
Right.
data.
Right, and but that's
Really
asking for every single category. Say, give me one.
Oh, and they
one,
also like
one
3 cars.
impression,
They do that
right?
for 3 cars.
Okay, yeah, but
and
that's
then they
3
do the-
cars. Okay, so
yeah.
if you want to compare, you know, that's 3 cars, 3 hours per car. That's 9 hours. If you want to
Per
compare,
person,
you know what I mean? Yeah,
times, like,
exactly.
couple hundred, yeah.
It explodes. You know,
Yeah,
in
it was like a
terms of the number of
10-day
things. Like,
thing
Yeah.
that it cost a
it
lot
just
of
seems
money.
like the cost of doing these pairwise comparisons is a bit significant.
Yeah, no, it is, and that's why, yeah, you don't want to have too many alternatives.
Right.
And so, you know, that suggests that maybe if you start off with a lot of alternatives, you want to use some of these other techniques to weed out the weak ones, the ones that are easy to throw those out ahead of time. And then with the criteria, the way to, you know, as I said, the way to keep that under control is to do it hierarchically rather than looking at all the criteria at once. Right. So when you look at software that's designed to do AHP, so like there's one we'll use in lab on Thursday that's an Excel workbook, and it has the ability to do up to an 8x8 comparison, and they don't even bother going higher than that because 8x8 is so what's the number of comparisons? It's going to be no, it's going to be 8 squared minus 8 over 2, right? So it's n squared. So you've got so the whole matrix is n squared, right? Take out the diagonal, that's n. So n squared minus n, and then you don't do the bottom half, so that's divided by 2. But it's still a big number. Yeah, and so typically what you do is when you're actually trying to elicit these opinions is you sort of set up the problem, and then if they're experienced, if they're experienced decision makers, and they you sort of get them engaged in the problem, then you can sort of leave them to do the pairwise comparisons themselves. If you're working with sort of consumer preferences, you probably have to go through and actually ask each of these questions one, which does get time consuming. Okay, so our skeptics here says, what about fuel economy? Do you do the same rating scheme for fuel economy?
I'm not sure.
Hmm?
I'm sure they did.
Well, what they said, because we actually have data on fuel economy, we don't have to elicit opinions. Okay, we've got the numbers for the 4 cars, and the standard way here is just to take those, and we just need to, those give kind of those are the relative scores in some sense, and so to get them to sum to 1 to match the others, you just divide each of them by the sum. Okay, and so. And so, by doing this as a ratio scale, it doesn't matter whether we measured them, whether the original data were in miles per gallon or kilometers per liter, right? There's once you normalize them, you're still going to get these same scores. On the other hand, if you went to Europe, where they measure fuel economy in liters per 100 kilometers, which is the reciprocal of the way we think about fuel economy, that is a very different way, a different scoring scale. And so then, so you do have to think a bit about what these numbers mean. Are they on a scale that makes sense? And implicitly, there's a 0 here, right? We're saying, if we compare these two, suppose this was 0.3 and this was 0.2, that says that the Civic has 50% better fuel economy than the Escort. Okay, and so that to be able to say that, there has to be a 0 that you're comparing them to. 6 is twice as good as a pH of 3.
That's really interesting. So with the mileage example, the miles per gallon, 0 miles per gallon makes sense. It's a car that doesn't run. But 0 liters per 100 kilometers is a perpetual motion machine.
Right.
So that doesn't make sense. So you have to flip the scale around.
Okay, so now we have our complete set of data, or scores, I guess, not really data. And so we take the numbers for each category, the scores for each car, put them into a matrix, and then apply this weight vector, right? And so that means that for the Civic, the final score is going to be 0.11 times 0.32 plus 0.379 times 0.558 plus 0.3 times 0.122, right? So just apply the weights to these scores to get a final value for the 4 cars, okay? And then you can just rank these. So the Clio has the highest rank, the Escort has the lowest rank, the Civic is close to the Clio, but not quite there.
And the example came from the UK, and the winner is a European Union car. So is there bias?
Who knows? Who knows? Yeah, I mean, who knows when they were making up those numbers, what they were trying to do. Okay, so here's our final ranking. So nothing about cost at this point. So we could have put costs in there and incorporated them as a criteria. At this point, I think this is no longer strictly an AHP concept. This is a more general concept about decision making. Should you be considering costs and benefits together at once, or sort of get a unified benefit ranking and a unified cost ranking and apply them and then compare them at the end? And these, the recommendation here is to treat them separately. And I think sort of psychologically, one reason to treat them separately is when you're eliciting information about benefit, for example, preferences. If the people you're talking to, are strongly sensitive to cost and they know what the least cost alternative is, they're going to color their stated preferences towards the lower cost alternative. And it's just there's kind of you get kind of a psychological crosstalk between costs and benefits that may not be that's going to lead to a less honest statement of what the actual values are. So there's if you've got costs and benefits, there's different ways of comparing them. And I don't know, have anybody or any of you taken cost benefit analysis? Yeah. So what are some of the ways that you deal with cost and benefits if you can reduce benefits to a monetary scale?
Net present value, benefit cost ratio, cost minimization. I think that's the only things we've covered in your lecture. So.
Okay, so you're taking it. Right. Yeah. All right. But basically you can plot benefits versus costs, and there's different ways of looking at it. You can try to make sure that you're on this frontier. Wait, is this the right frontier? Low. No, actually, you want to be on this frontier, right? You want the most benefits for a given level of costs. Or you can calculate, which has the best, is most cost effective in terms of cost benefit ratios. If you've got a fixed budget, you know, you can't afford that alternative, right? So in this case, they use benefit to cost ratio. So here's the prices, which don't look like European prices. They don't even look like American prices. And you just divide the, then they normalize them to 1 and divide them by, divide these normalized costs into the benefit scores. And so when you do that, specific comes out. That score is still last. So that's basically sort of stepping through doing an AHP analysis. So what we can do, the power of the hierarchy is, within one of those top level criteria, we can actually say, well, there are a bunch of sub criteria that go into that. Okay, so we talked about reliability before, but suppose. Suppose for style, we cared about the exterior style, the interior style, the comfort, and the number of drink holders. Right, those were our sub-criteria for style. Okay, so we could then again essentially run a whole separate AHP process to weight those and to get scores for those. Okay, and so. And the power of doing that is that we don't have to compare each of those sub-criteria to reliability and fuel economy. We just have to compare them to each other. So within style, we're going to have these 4 criteria, and those are going to have sub-weights that sum to 1. So perhaps 0.4 for exterior style, 0.1 for interior style, 0.2 for comfort, 0.3 for non-drink holders. And then, and then to get the total score for that criterion, you just take, say, 0.3 for exterior, for 0.3 for drink holders, and multiply it by the score that we got, the total, the aggregate score that we had for style, which was whatever it was, 0.3. And that product then is going to tell you what the weight of drink holders is relative to these that are top level things.
Okay. So this was obviously to decide which car to buy, but could you also include the alternative like mass transit, monthly bus pass, in this decision? Could you have done that, formulated it that way, and then figured out if actually purchasing a car or purchasing a monthly bus pass, or rail pass would have been
Okay,
the
so
preferred option?
what do you think?
You just have to ask.
I think probably not, because
I think you can. You just have to raise your goal. You just say the goal is not the best alternative, the best
It's the-
method, and then come back.
the best mode of
Yeah, you just
transportation.
keep,
Right,
yeah.
okay.
So if you have sub-criteria, you still have to do the pairwise comparisons for the higher criteria.
Right. So what you'd
separately.
have is you'd have the pairwise. You do all the pairwise comparisons with the top 3 criteria, and then if under criterion 1 you had 3 sub-criteria, then you would do the pairwise comparisons of those 3 sub-criteria. But you only have to compare them to each other, right? So it doesn't. You don't have this exploding number of comparisons, right? By adding these 3 sub-comparisons, subcategories, you've only added 3 additional comparisons you have to make, instead of, you're not expanding your matrix by 3, right? You're sort of building a matrix, a sub-matrix into the existing matrix, but it's isolated. True?
That's a really good example of baking off, car versus bus versus just baking off car. Because but when I talk about this in 263, which I don't get to go into any real depth on, but it's always about the beauty of this process is that it gets people to argue about stuff where they know what they're disagreeing over. So when you're arguing about a car, you're just arguing about whether which car has the best fuel economy or has the best this or the best that. By the time you're arguing car versus bus, the nature of a car and the nature of a bus is settled. You know what the best car is. You know what the best bus is. Then all you're arguing about is whether a car is better than a bus. So you focus your disagreements. I mean, it sounds counterintuitive, but basically when people are arguing about something, you want them to be crystal clear about what they're disagreeing on. I weight a bus higher than a car for these reasons, and I weight a car higher than a bus for these reasons, and it's all out there. You can see it. It's not like, I don't like cars because cars are more expensive than buses. No. We haven't got there yet. We're disagreeing on just other attributes of them, and so it focuses it in so that, you expect there to be disagreement in the process, but you basically come out with multiple models for what the disagreements are. So this is a really good example.
And so you avoid the situation where somebody says, I'm having my midlife crisis. I want my red sports car no matter what. So I'm just going to skew the discussion around to make sure the red sports cars come out on top.
Also, I think with that, I almost envision multi-criteria on top of AHP. So you do individual evaluation with AHP, and then you compare those with multi-criteria.
Exactly.
Or you could even do AHP on the higher level
Yeah.
if you wanted to,
Uh-huh.
right? I mean, so the hierarchical aspect can be done in any of these approaches, and you can sort of mix and match. And in practice, you can kind of mix and match techniques at the different levels. The proponents of AHP, the sort of AHP purists, might disagree with you, but in practice, there's a lot of mixing and matching that gets done. And so the commercial software for decision support usually has a bunch of techniques plugged together, and you can sort of mix and match in there.
Bruce, did you ever, when you were working on reserve design, did you guys ever use this in public forums or anything like that?
I wasn't at any of the forums where they were sort of eliciting what the evaluation criteria would be. So I don't know how that was done. Probably not. It was probably more of just a kind of guided conversation. There never was a kind of weighting scheme applied to these criteria. It just said, here are the criteria that were agreed upon by the stakeholders. And then when the science panel was evaluating various proposals, they just said, well, here's how it scored on the first criteria.